So in the previous two parts of the lecture, I have explained to you how you can combine two solutions of your RK4 using two different step sizes to get a more accurate solution for your RK4. That is actually based on your Richardson's extrapolation concept. And from there, we have also derived the expression to quantify the error estimate of two RK4 solutions. And we have seen that decreasing the step size for us to get a more accurate solution may not always be the case, because it may not be efficient, since decreasing the step size will also mean that you will have to increase the number of points or number of steps that you're going to use in your solution. So we already see how we can actually link the expression for our H0 and our HC, and doing so would actually help us to produce an adaptive step size algorithm that will not only ensure the accuracy of your solution, but it will also maintain the efficiency of your numerical algorithm. So how does the adaptive step size algorithm actually works? So we are going to code the RK4 as usual. So you're going to perform your RK4 with a particular step size. So let's say you start off your RK4 with a step size of HC. So this will be calculated not for the entire step. So if the question asks you to calculate from 0 to t, or let's say 0 to 10 seconds, you're not going to calculate the solution for 0 to 10 seconds for your step size of HC. You are just going to calculate for one step, and you move on to step size of HC. Okay, so you perform your RK4 for one step using a step size of HC. Once you have done this, you are going to perform your RK4 again, but this time you are going to halve the step size. So if your initial step size is, let's say, 0.1, you're going to repeat the RK4 using 0.05 or 0.1/2. Just bear in mind that when you decrease the step size to HC/2, you need to do your RK4 two times in order for you to reach the same time step as the case when you use step size of HC. So once you have performed these two solutions using these two RK4, you can then calculate the current error that you have. So the current error, if you recall from our previous slide, delta C, yes, delta C is basically given by this, but this equation here would not be useful to us. If we already have two solutions from our RK4, delta C is essentially just the difference of your two RK4 solutions, one obtained using HC, the other one using HC/2. So what you're going to do is you are going to calculate your delta C, or your current error, by taking the difference in your solution. Once you have this delta C, you're next going to use this expression that you have for the optimum step size. Alright, so you're going to use this equation to calculate what is H0. You know HC, you know delta C, you know delta naught, because delta naught is the tolerance that you are going to use. So from here you can estimate what is H0. So once you have your H0, you're going to do an if statement to actually check whether your error is larger or smaller than the tolerance. So in the case where your current error is smaller than the tolerance that you choose, you are going to set HC to be equals to H0, and you're going to move on to the next step. So when you move on to the next step, it means that you're going to repeat RK4 right now, but with the new HC that you have selected. Okay, so if this is smaller than delta naught, this is what you're going to do. And if delta C is greater than delta naught, you are also going to set HC to be equals to H0, and then you're going to repeat not the next step, but the current step. So when you look at this, you might be wondering, we are going to apply HC to be equals to H0 anyway, so what is the purpose of this checking? In the first case, when delta C is less than delta naught, the current error being less than the tolerance actually tells us that the step size that we choose is smaller than the optimum step size that we should use. So it means that if you keep continuing with the current step size that you have selected initially, you're going to get a not efficient algorithm, just because the step size that you choose is already smaller. So what we do is we increase the step size from HC to H0 and we move on to the next step. So in your next step, you are going to use a larger step size to hopefully reduce the number of steps that you need. And in the case when the current error is larger than the tolerance, it means that the HC that you select is probably too large, which causes the current error to be larger than the tolerance that you choose. So if your current error is larger, it means that your HC is actually too large. What happens if you use a step size that is too large? It means that the solution that you get for that step is not accurate. That is why you have to set HC to be equals to H0. When you set HC to be equals to H0, you don't move on to the next step. This is because the next step would have had the current step would have had a large error. So you need to repeat the current step using the optimum step before you actually move on to the next step. So when you actually do this in MATLAB, you because this is a condition that keeps on repeating, you probably have a while loop that will loop until you reach your final time. Okay, so when you do your while loop, what you're going to do is you're first going to, so I'm not going to write the MATLAB code, I'm just going to write like a pseudo code so that you can understand how we actually implement this. So within your while loop, you usually run an RK4 that is done using a step size of HC. So this, you are going to call it Y1. So you're going to call your RK4 function to solve it for one step. Then you're going to halve the step size, and then you're going to call your RK4 again. But bear in mind, you need to call your RK4 2 times. Okay, so once you get your Y2, which is the solution of RK4 2 times, you can get your delta C, which is just your Y2 minus Y1, and then you have your error checking. So if this is less than tolerance, it means that your results is good, just that your step size is too large. So if your step size is too large, then you will have to change your step size to the, sorry, your step size is too small, so you have to change your step size to the largest step size that you have, following the criteria that we have. And of course, you have the else statement where your delta C is going to be larger than your tolerance. So in this case, you need to again change your HC to your H0. Now, in the case when this condition is satisfied, so let me get rid of this. In the case when this condition is satisfied, it means that your HC is actually small enough such that the error estimate is smaller than your tolerance. So you can set your Y, how to put it? So you can set your Y current. So Y current is actually the solution at the current time step to be your Y2. But since you already have Y1 and Y2, rather than just taking the solution of Y2 as your solution, you can further improve the accuracy by using Richardson's extrapolation. So what I mean by that is, you already have Y1 and Y2. You can further improve the accuracy by performing this Richardson's extrapolation, because this would have been your Y2, the solution that you get with step size of H02. This would have been your Y1. So within your code here, if this condition is satisfied, you can further improve the accuracy by taking 16 over 15 of Y2 minus Y1 over 15. Then here you cannot do anything. You're going to apply the check, and then you're going to repeat the step. Here you are going to put a condition that will increase the step to the next step. Alright, so I hope a pseudo code like this will give you an idea. Of course, if you're just sitting down listening to this, it might not be that clear. My suggestion to you is to try to think of what is being written here and try to relate to the code or the pseudo code that I'm trying to explain in this particular slide. So theoretically, this is what we would do. However, if you look at a lot of numerical method handbooks or textbooks, you'll find that in our implementation of the adaptive step size control, we usually write H0 given by these two expressions here, depending on whether delta C is greater or smaller than delta naught. So the difference here is that if delta C is less than delta naught, the power is 0.2. So 0.2 is effectively the same as 1 over 5. Okay, and if delta C is greater than delta naught, we use 1/4. So these are coefficients that people have found through various numerical experiments, and they found that doing so would actually help improve the efficiency and the accuracy of your adaptive RK4. So these are the two differences for more practical numerical implementation. The other one is there's a coefficient or factor introduced in front of here. So this is what we call a safety factor, and we usually take it as 0.9. So we want the H0 that we choose to be slightly smaller, just in case we get cases where the error is near the threshold that we set according to this equation. So having a safety factor of 0.9 would force the H0 to be smaller than the exact threshold that we have. So this will again also help to improve the accuracy and the efficiency of your adaptive RK4. So this is a summary slide which you can read it. So this is it for lecture 16.